we're going to look at applications now of the random walking in 3D. So we've already seen that the displacement d of a particle randomly moving in a gas would basically be equal to square root of 2n times the mean free path. And we've seen that the mean free path is simply equal to 1 over square root of 2 times n sigma, sigma being the cross-section of a molecule. Now, we'll need to consider certain conditions, so we're going to assume that we're dealing with an ideal gas. And in other words, we're dealing with an ideal gas, nkb times T. And in other words, we could express N, the number density, in terms of the pressure and the temperature. And thus, I could rewrite lambda as 1 over square root of 2 P. So I'm going to have Kb times T on top, and then I'm going to have something like square root of 2 of P times sigma. And then if I replace in the expression of the displacement d of the molecule after a certain time t, it's going to be equal to Kb times T over P sigma times the square root of n, n being the number of steps. Again, if I want to make sure I understand that, this is the number of steps. Okay, now that's one thing that's already taken. The question is, we're going to put a distance, and we're going to ask ourselves, how many steps do we need, and what is the distance that it's going to be to travel. So let's put some assumptions. Let's say we're dealing with a room where the distance is 5 meters. So we're looking at how much time it's going to take for a molecule to cross the room, going into completely random directions, so collisions all the time. We're going to take the pressure to be 1 atmosphere, which is basically 1.01 times 10 to the 5 Pascal. So it's 100 kilopascal approximately. And then we're going to talk about a molecule of oxygen. Now the size, you'd go on the internet, you'd find it to be approximately 0.99 nanometers. That's the diameter. So that's D of the molecule of oxygen. Okay, now what does that allow us to compute? And the temperature, we're going to assume the temperature is basically 20 degrees Celsius, which is basically 293 kelvins. And just for you to know, the Boltzmann constant is 1.38 times 10 to the minus 23, and it's joules Kelvin per Kelvin. Okay, now if I do express all these things, I'm going to end up with the square root of n being equal to d pressure omega divided by Kb times T. And if I square that, I get n equals the square of all this. Okay, what is the cross-section? In my situation, the cross-section is simply equal to pi d squared, d being the size of the molecule of O2. So I'm assuming that it's approximated by a sphere. Fine. Now, I'll do the computations. And what do I find? Okay, then, calculations, we get n equals 1.23 times 10 to the power of 15. Now you see, we're already talking about very large collisions. We're talking about a distance of 5 meters. Now, the second thing you could compute is basically tau, the average time per collision, and then multiply by the number of collisions. So you end up with the total time it takes to travel a distance of 10 meters. Now, what is the expression for tau? We've already seen that tau then tau, oops, something is, okay. Tau is simply equal to 1 over n sigma and the average relative velocity, which we found to be equal to the square root of 2 of V average. Now, V average is calculated from the Boltzmann distribution by something like the integral of V, the Boltzmann distribution dV, right, taken from 0 to infinity. And then you'd find it, again, you could find it in textbook or any other book on that, or you could basically compute it. It's 8 over pi KEB times T over m, where m is the mass of one particle. In that situation, the mass of O2 is essentially equal to 32. Now, I need to express things in kilograms, so it's 1 times 1.66 times 10 to the minus 27 kilograms. Let me make sure that that's clear. Okay, now, once you do the math, you do the replacements, etc., you're going to find that tau is of the order of 10 to the minus 10 seconds. So it's 2.29. So it's about 2.29 times 10 to the minus 10 seconds. And the total time taken is simply n times tau, which is the time between collisions, the average time between collisions, and it's going to get, once you do the math, it's going to be about 3.26. Okay, now you might expect I'm going to write seconds. Actually, I did the conversion. Days. So the times are very long. Now, if you'd like to know how long that is, you could compare basically the total time had it been flying straight. So assume that O2 is moving with the average velocity V bar that we've calculated, square root of 8 over pi kb t over m, and it's going straight over the 5 meters. So I'm going to compare that to the flying time, which would be 5 divided by V average. And if you do the math, you're going to find that V average is about 440 meters per second, approximately. And you're going to get something like 0.01 seconds. So it's a bit larger than this. It's 0.011 seconds. Now compare these two numbers. And now it shows you this with that, right? And that shows you basically how much diffusion is a slow process. It's a very slow process. Now you're going to say that when we feel a smell, it doesn't take that long to get there. But don't forget that you've got temperature differences in a room. Temperature differences create pressure differences, and pressure differences would create a bulk motion of the air in the room. That would actually help carry the smell or whatever there is here. But the idea is that the basic process, if it was basically just random motion, that's a very slow process that plays a role. Okay, with that I've concluded this issue of random motion. We're going to go over applications and things like that, but that's the crux of the matter. Applications are numerous. Once you look at diffusion processes play a role in a number of places, especially when you have a lot of time, like stars, for example. Some people believe that diffusion processes could play a role in changing the concentration of a number of elements in different layers of the star, etc. Anyway, if you're interested, that's a topic for another discussion.